Jai Hind everyone, I am Navjyoti Sharma once again in front of you to take some of the numericals based on unit 3, which is transformers in AKTU. So we'll be continuing with the certain numericals as well as with certain theory questions which have occurred in the very recent previous AKTU question papers. The very first numerical, if at all I go with, is say a transformer working on no load has a core loss of 50 watts. It draws a current of 2 amperes and has an induced EMF of 230 volts. Determine the no load power factor, core loss current and magnetizing current. Also calculate the no load circuit parameters of the transformer. Neglect the winding resistance and leakage flux. So this is a question which repeatedly used to come in AKTU and is I must be saying is under the topic of equivalent circuit or the no load circuit of the transformer, right. So what are the given things in the numerical is that the no load core loss is 50 watts. We know that at no load condition, whatever is the power taken by the transformer is majorly going for the iron loss and a very negligible amount of copper loss, as the no load current is very small. It is I0. It is the no load current and used to be just 2 to 3% of the full load current, which is a very small negligible value. And when we go for the copper loss, I0 square R1, right. It's a no load. Secondary side there is no load, there is no secondary current. So in the primary it is only the no load current, so I0 square R1. So that power is a very small power. So the copper losses are very negligible. So we can be saying the complete power taken by the transformer is only the iron loss, and that has been given to us. So the no load core loss is given by 50 watts. Fine. The no load current at the no load, what the transformer is taking, the current, that is also 2 ampere, right, and the input voltage is 230 voltage. So if that's so, at no load we know that the power taken would be given by, once again it's an active power, it has to be VI cos phi, or when it is an input power, so it will be V1 I1 cos phi. What is V1? It's E1, that is 230. I1 at no load, what is the input current? The input current is the no load current, I0, and the no load power factor, right. So the no load power factor which we need to find out would be given by obviously the input power, which is nothing but the iron losses, which is nothing but 50 watts divided by even I0, right. So that will be 50 upon 230 is the input voltage multiplied by the no load current, that is 2. So that will be 0.1086, which is almost equivalent to 0.11 amperes. Now, what is the core loss current, right? As we know, if we go with the no load working of the transformer, no load phasor diagram of the transformer, this no load current consists of two currents, two components. One is the magnetizing current, which is responsible for the magnetization of the core or for establishing the flux in the core, and the another one is the working component or the core loss component, right. So the same is being asked over here. What is the core loss current, IC, which is nothing but the sine component. So it will be given by I0 sine phi naught. It is 0.11. The cos phi naught is 0.11. So the sine phi naught would be given by 0.99, right. So the IC is given by twice into 0.99, that will give me 1.98 amperes. So the power factor, what we got it as 0.11, and the core loss component what we got is 1.98 amperes. Now another one is the magnetizing component, that is IM. So IM is the cos component, So we need to go for the Im, that is I naught cos phi naught. So that will be twice into 0.11. So that will be given by 0.22 amperes. Now the no load circuit parameters, if you just see the numerical, in this the things which we need to determine, the very first thing is the no load power factor. One is the no load power factor, we have found it off as 0.11. Then we need to find the core loss current, that is IC. We have found it out as 1.98. Then we need to find the magnetizing current, that is IM, right, which is responsible for the production of the flux. So that is, once again we have found it off in likewise 0.22. Now the question desires also calculate the no load circuit parameters of the transformer, neglecting the winding resistance and leakage flux. So if we just see the no load circuit parameters, what are the no load circuit parameters? You know, if at all I just go with the no load circuit, this is supposed to be the input voltage. This is the no load circuit of the transformer. I know this no load current is actually consisting of two currents. One is the magnetizing current and another one is the core loss component, right? And the core loss component is the active component and the magnetizing current is the reactive component, right? Given this core loss component is given by say R naught and this is given by XM, right? So if at all I see what is the voltage across these two components, that is nothing but V1. Now the question desires what are these components, R naught and XM, right? So the question as it is read, calculate the no load circuit parameters of the transformer. We had no load circuit parameters, we have found it of I naught, we have found IC, we have found IM. Now we need to find R naught and X naught. So it will be XM would be given by directly the input voltage E1 divided by IM. So it is 230 divided by 0.22, so that is 1045 ohms. And similarly the core loss resistance, that is Ri, that will be given by EI upon IC, that is 230 divided by 1.98, it is 116.16 ohms. Just to finish off, because this question demands, and in the university AKTU also, there has been many of the theory questions in which the equivalent circuit of the transformer is being asked. So first we will, after this question, will be going with the equivalent circuit of the transformer. And if we see what is the requirement of this equivalent circuit, what is the requirement of this equivalent circuit? So while studying, if you just see, while studying the performance analysis of a transformer, you know, we need to have its working being done in certain parameters, right? To have those parameters, to have the efficiency of the transformer, to have the voltage regulation of the transformer, how it is working, to have all those analysis, we need to have the complete transformer being given like a circuit, right? Its resistance, its winding resistance being given like a circuit, its leakage reactance being given like in a circuit, right? So we'll be forming an equivalent circuit of a transformer, and it may be given in various ways. Likewise, the very first one is the exact equivalent circuit of the transformer. The way the transformer is, and how the transformer is having its two windings. One is primary winding, one is secondary winding. Both the windings are electrically isolated, right, but magnetically coupled by a common magnetic core, right? So the same way we'll be drawing the exact equivalent circuit. What we are drawing right now is an exact equivalent circuit, right? So if you just see the exact equivalent circuit will be starting from here, or I must say will be starting from center. This is the symbolic representation for a transformer, right? This is a symbolic representation for a transformer. Presently, I am not stating it as a step up or step down. So it is a single phase transformer, a two winding transformer, mutually coupled by a common magnetic core, right? The side to which it's a bilateral device, the side to which I'll be providing the supply would be the primary, and the side to which I'll be connecting the load would be secondary. Say I'm connecting the supply towards this side. So this side, this becomes primary. Now, if this is primary, it should start with the supply. Obviously, it's an alternating supply and AC needs to be fed to it. Say V1 is the input voltage, right, being given to the transformer. As we know, the VA rating of the transformer is given by some V1 I1 or V2 I2, where V1 I1 and V2 I2 are the rated input side parameters and output side parameters, right? So if V1 is the input voltage, I1 is the input current, right, or the primary current of the transformer. We once again know that this input current is basically the phasor addition of two currents, I0 and I2 dash, where I0 is the no load current and I2 dash is that extra current taken by the transformer when loaded compared to the no load condition, right? So once again it is the addition of two currents, I0 and I2 dash. Now the primary winding resistance, say that is R1. R1 is the primary winding resistance, and then the leakage reactance X1. The leakage reactance, which is actually giving us the drop which is occurring because of the leakage flux, right? It happens on both the sides, primary as well as secondary side. The leakage flux definitely is going to get us the voltage drop. So this leakage reactance, this is a fictitious reactance which is actually being introduced to represent the voltage drop which is occurring because of that leakage flux, right? Now the no load current, once again we come back to the numerical part what we have just gone for it, that once again this no load current is the phasor addition of two currents. One is IM, the magnetizing current, and the another one the core loss component, right? So once again it is consisting of two, the reactive component X0 this is X0 and this is R0, right? This current is being called as the magnetizing, and the current which is actually going for the work, which is taking care of the losses. Losses, which losses? The copper losses, which are negligible because the no load current is very small. So a very negligible amount of copper loss and the major iron loss or the core loss. That's why we used to call it as core loss component IC. Right? This is I2 dash, which will be giving us the induced EMF in the primary, say E1, right? Now, when this induced EMF, because of the mutual induction, the secondary will also have an induced EMF given by E2. Now, this E2 will drive the secondary circuit, and in this secondary circuit, what will be having? Once again, the secondary winding resistance. The secondary winding resistance is given by R2. Leakage reactance of the secondary is given by X2. And finally, our load ZL. right? It will drive this load circuit, so it will be having a current of I2, and similarly we'll be having the terminal voltage across the load as V2. So this is the circuit, what we call it as the exact equivalent circuit of the transformer. Right, from this very circuit itself, we used to draw the phasor diagram, have the relationship between V1 and E1 as well. From seeing this, we can be knowing what is the relationship between V1 and E1, right? If at all there is nothing in between, if at all I consider there is nothing in between, it is not loaded, it is not drawing any current, in that case, if it is a no load circuit, only no load current is there and it's also very negligible, then V1 must be equals to minus of E1. But when it is loaded, the transformer will draw the current I1. In that case, what will happen? V1 is equals to minus of E1 plus the two drops, the two major drops. What are the two major drops? I1 R1 and I1 X1. These two are the major drops. Now this is the exact equivalent circuit. Now coming to, while going for the calculation or the analysis purpose, as we can see, we are having two different circuits. So while going for the analysis purpose, it becomes tedious job to go for two different circuits and analyze them separately. So it's better that we combine both of the circuits and make it a single circuit, right? There coins the terms referred value. So what we can do is we can refer the complete secondary circuit towards the primary circuit, or we can refer complete primary circuit towards the secondary circuit. So that gives us the second equivalent circuit of the transformer, which we call it as equivalent circuit of the transformer referred to primary. It is the equivalent circuit of transformer, referred to primary, right? So that means the primary is as it is there, and the secondary circuit, completely secondary circuit, is being referred towards primary. So if at all we see once again from here, so the primary circuit is as it is. Input voltage is V1, input current is I1, it's flowing in the primary resistance R1, leakage reactance X1, the no load current I0, the no load current is once again divided into IM and IC, IM having X0, IC having R0. This is as it is, the primary circuit is as it is. Now this is I2 dash, right? Now the mutual coupling is removed. There is no different isolation between primary and secondary circuit. It will be submerged in the primary circuit, but with the referred value, so that its significance is not lost. That means the losses what the secondary resistance were making in secondary side, the same effect it will be producing when it is being referred towards the primary side, right? If we do that calculations, then obviously the secondary resistance will turn out to be a new resistance, say R2 dash, and how its value is going to get changed? It is going to change by R2 by K square. Well, what is K? K is the transformation ratio of the transformer and is defined as secondary turns by primary turns, or the secondary voltage by primary voltage, or the primary current by the secondary current. What we call it as turns ratio, current ratio, voltage ratio, and finally the transformation ratio. Similarly, the reactance will also get changed, X2 dash given by X2 by K square. Then once again the load, see that is ZL, it will be changed to ZL square. As you can see, components of the loads, likewise the resistance, the reactance, when you refer them towards the primary side, their values are changed by k square. Their values are varied by divided by k square. So once again, the impedance when it is referred to as the primary side, the load impedance, it will be divided by k square. Then the secondary current I2, that itself has changed. I2 has changed to dash, but by how much value, right? So we already know this relation, that this I2 dash, which is the current taken by the transformer, I2 dash, that is equals to minus of k times of I2 in phasor. Right? So that is k times I2. Right? Now the one thing which is remaining is once again the terminal voltage V2 dash. That would be equals to the original terminal voltage which was there in case of when it was in exact circuit. So it will be V2 by K. One more thing is remaining. What is that? We haven't represented the induced EMF right now. Where would be the induced EMFs? Here. I can represent it over here. This is E1 and is also equals to E2 dash. And what is E2 dash given by? E2 dash is given by once again E2 by K. So this is the equivalent circuit of the transformer referred to primary, in which we haven't changed anything towards the primary side. The primary side of the transformer is remaining same, but we have referred completely the secondary parameters towards the primary side. Now similarly, the third would be the third kind, in fact in the same. Now if we just see, for calculation purpose, right, we require the equivalent resistance of the transformer, either referred towards primary or referred towards secondary. Likewise, if at all we want to calculate the total copper losses of the transformer, right, or the efficiency of the transformer, where we require the total copper losses of the transformer. So that is given by, if you just remember, the total copper losses of the transformer is given by, total copper losses of the transformer is given by I1 square R1 plus I2 square R2, either by the basic formula, or when it is referred, I may be going it with R1E. What is this R1E? This is the equivalent resistance of the transformer referred towards primary, right? If that is so, so in this equivalent circuit, there is no R1. I am not able to find the equivalent. We have referred the complete circuit towards the primary, but I am not able to find the equivalent resistance of the transformer referred to primary. Similarly, I am not able to find the equivalent reactance of the transformer referred to primary. I am not able to find the equivalent impedance to find, if at all I want to have the total voltage regulation of the transformer, or how much is the total impedance of the transformer referred to primary, I am not able to find it off, right? So what is the requirement for it? But if you just see in this, I can be going for R1E. What is R1E? It is the equivalent resistance of the transformer referred towards primary, and this R1E is given by R1 plus R2 dash. That means when R2 dash is being added to R1, right? And this is only possible, I may add this R2 dash and this R1 only when they two are on the same side, right? They are completely in series, right? Right now there are two different currents, these two are not exactly in series. So to have them in series, and so that we can be able to add them to have the equivalent resistance, a minor approximation is being considered in equivalent circuit, and then the third equivalent circuit is being given, which is being called as approximate equivalent circuit of of the transformer referred towards primary, approximate equivalent circuit. So how the approximate equivalent circuit is being drawn? With certain amount of approximation being made, that this no load circuit is being shifted, and deliberately an error is being created, and this no load circuit is shifted prior to R1 X1. or I may say this R1 and X1 are shifted towards the right hand side of the no load circuit, right? So that now if at all I do so, I shift this resistance and reactance towards the secondary side, or towards this side of the no load circuit, not towards the secondary side but towards the no load circuit of the transformer. In this case, what will happen now? I'll be having R1 here and I'll be having R2 X1 here. We'll be having X1 here, right? Now if we just see, now this becomes easier now, right? Now we can combine R1 and R2 dash. Combiningly R1 and R2 dash will give me R1E, the equivalent resistance of the transformer referred towards primary. Similarly, this X1 and X2 dash will give me X1E, equivalent reactance of the transformer referred towards primary, and combiningly these two will give me Z1E, which is given by R1E plus J X1E. This gives me the equivalent impedance of the transformer referred towards primary. So this circuit becomes now the approximate equivalent circuit of the transformer referred towards primary. This is the question which has occurred many a times in AKTU for drawing the equivalent circuit, approximate equivalent circuit of the transformer referred towards primary. So I have given you the basics regarding how to draw the exact equivalent circuit, then referred towards primary, then the approximate equivalent circuit referred towards the primary. In the coming videos, we once again will be starting with rest of the numericals, the theory based on those numericals. Thank you so very much.